oh, hold on a second, get something I need to do first. Just to stop any background noise. So you're going to have to hit the space bar if you want to say anything, which I would love you to do, so I don't feel like I'm on my own. So we're going to do chapter 11. Hopefully we'll do all of it today. We'll see how that goes. Taylor's and Maclaurin series, that's essentially it. What these two guys managed to do was to come up with a way of finding the power series for any function in the world. Maclaurin series basically says that the function f of x can be written as this series. You know, x to the n basically just gives you your powers of x. So when n is 0, you get a constant. Then in n is 1, you get the x term. 2, you get the x squared term to eternity. And if you cover that up, this bit here, that's basically the coefficient of the power of x. So if you want to know what does x to the n have on it, right, the x to the 10 term, then just find the 10th derivative at 0 and divide it by 10 factorial. We also talked a little bit yesterday about the fact that most power series, the early terms are where all the value is. So if you take a power series and you do just the first 4 or 6 terms, depends on how quickly it converges, you will get a pretty decent value to your function. Now I think, and I'm just doing it by memory, which is scary, but didn't I do some quite impressive accuracy? I think I did some like the sine of 0.12345, and we did it with whatever it was, 4 terms probably, and it ended up being like 8 decimal places good. And considering it's only a polynomial of 4 terms, I think that's pretty impressive. I think we tried to do with e to the x, we tried to do e to the 1. E to the 1 wasn't that good. Agreed. It was about 2.6 and it should have been 2.7128. But e to the, e to the x would have been better if I'd done 10 terms, 20 terms, whatever it takes. So some terminology. Maclaurin series is centered at x equals 0. Essentially, that guy there is 0, and this fella here is on his own. Technically, he's x minus 0, but on his own. And then, essentially, all Taylor did was he went with what Maclaurin had discovered and he expanded it. He went and said, well, that's a good power series. We all like powers, polynomials to be x's and x cubed, but sometimes that's not possible. Is there a way that we can write a power series centered at a different number? And so this is Taylor's series is basically Maclaurin series, but centered at a. To which my mind is saying, why does this guy even get a name? I mean, this is a heavy duty lifting, isn't it? This is just an extension. And normally you don't get something named after yourself if all you did was take somebody else's bright idea and like tweak it a little bit. But evidently people thought that that was such a cool trick that it deserves getting named after the person who created it. So what are the types of questions that you're expected to do? Well, we've touched on that a little bit. I think I proved e to the x, if my memory serves me correct. Did I do the power series for e to the x? So some of the questions are going to be create a power series, either Maclaurin's or a Taylor's. And those are quite hard. You might think that they're not, but they are. And the reason why they're quite difficult isn't that we don't know how to differentiate things. That's probably the easy part. And it's not that we can't evaluate them at 0. What the problem is trying to find a generalized formula for the nth derivative at 0. Because we need to have a generalized formula. In other words, when n is 42, this is what it is. When n is 40 million, this is what it is. When n is n, this is what this is. And that's the hard part, because that's a process of trying to create a pattern from what sometimes looks like random digits. So let's start with that kind of question. I'm going to choose one of my friends, because this is one of the easiest ones to do. And then I'm going to try and do some ugly ones. So the question is, find the power series centered at a equals 0. Basically, find Maclaurin series. Well, you find the first derivative, you find the second derivative. You keep finding derivatives till you think you can see a pattern. Right, e to the 3x, e to the 3 nothings, e to the nothing, 1. First derivative, 3e to the 3x. The first derivative evaluated at 0 is 3. Second derivative, this is somewhere you have to be a little bit more careful. The temptation would be just to do, you know, chain rule and call that 9. If you do and you call it 9, you're going to find it much harder to do the nth formula. So when you create these things, try not to evaluate things. Just try and write down the calculation that it would need to be. Would you agree that this fella would end up being 3 squared e to the 3x? It'd be 3 times e to the 3x times another 3. Agreed? And when you evaluate this derivative at 0, don't call it 9, call it 3 squared. Right, one more one. I think this should be enough to do it. Would you agree the third derivative, which is basically this guy being differentiated, would you agree that it would end up being 3 cubed, e to the 3x, and so the third derivative at 0 would be 3 cubed. And now the tricky part. If you kept going for the 20th derivative, the 2 millionth derivative, what would the nth derivative be? Well, they all have an e to the 3x in it, so I'm pretty comfortable I know that's going to be the answer. Would you all agree that they're going to be 3 to the power or something because of the way I've written it? And then I look for patterns, and thankfully, because this is a nice function, that pattern is pretty easy. Would you agree the second derivative gets you 3 squared, and the third derivative gets you 3 cubed, so shouldn't the nth derivative get you 3 to the n? Great. Now, what's this fella going to be worth when x is 0? Well, it's going to be 3 to the n times 1 is going to be 3 to the n. We have now got the power series for e to the 3x. It's sigma n equals 0 to infinity, the nth derivative at 0, x to the n over n factorial. So I've just created from scratch a power series for e to the 3x. You like it? It's a process. Okay. Well, that's considered an easy one because I think it is. Let's try and find a Maclaurin series. For cosine x. And let's center it at 0, which means it's a Maclaurin series. I guess I should start again because I need more room. That wasn't too painful. If you find the first derivative, if you differentiate cosine x, don't you get negative sine x? And the derivative, oh, sorry, that's not f, it's just f. The first derivative at 0 is negative sine of nothing, it's nothing. If you do the second derivative, you get negative cosine x. The second derivative at 0 ends up being negative 1. If you do the third derivative, you get negative in cosine gives you, and you get positive sine x. And that guy at 0 gets you 0. If you do the fourth derivative, oh, you get back to cosine x. And so the answer is 1. These derivatives evaluated at zeros have a very distinct pattern to them. Isn't every second one 0? And the ones that are numbers, aren't they either 1 or negative 1? I'm very cryptic here. You're going to have a big problem trying to create a formula that gives you a 1, then gives you a 0, then gives you a negative 1, then gives you 0, then gives you a 1. So I'm not going to. What I'm going to do is I'm going to look at the first derivative gives me this guy, and the third, get this 1, 2. Second derivative gives me that guy. Fourth derivative gives me that guy. Won't the sixth derivative give me that guy? And won't the 10th derivative, or the 8th, I should say the next one up, give me that? And won't the 10th derivative give me that? So the pattern that I have noticed is that only even derivatives have numbers. And the numbers that they are just 1 and negative 1. So I know how to create a 1, negative 1 deal. Can't you just take negative 1 to the power of something? And if you take it to the power of, say, n, won't that generate 1s and negative 1s depending on the value that we've got? And so far, so good. Now, if I do this guy here, and this is the leap, when n is 1, won't the derivative be the second derivative here? And if you plug in 1 for the second derivative, won't you get negative 1? Let's see if this generates that pattern. I want to know that, I'll pick somebody. I want to know that the sixth derivative is negative 1, right? To get the sixth derivative, don't you use n is 3? And it works. So this shows you why these things are so difficult to create. Here is my fella. That fella. So we're going to do n equals 0 to infinity. We are going to be putting in negative 1 to the n, x to the 2n over 2n factorial. And you're saying, why are all these 2n's being used? Because that guy only uses multiples of 2. Do you see what I've done here is I've avoided all the odd powers of x because they're all 0. But because I've done that, I've had to re-parameterize the exponents. In other words, it's not x to the n, I have to use x to the 2n. That is the cosine of x. And that is horrendously ugly. And that's just the cosine. If you did the sine function, But let's just show you some of them. E to the x is the only one that is actually, in my opinion, pretty easy to do. Cosine x is the one we just discovered. Here is sine x. How do you, can you have a guesstimate? And that's really all it is right now. What the power series for sine x might look like, because it would have a very similar kind of situation in that cosine one that we just fought our way through. But what would be the major difference? You know how the cosine uses even powers of x only because the other ones are zeros? What do you think a sine x uses?
Powers.
Right? And to generate the odd powers, it looks like that. If you look at sine x and cosine x, you see that their power series are similar. They're not the same. But do you see what the cosine does is it uses all the even powers and alternates them. And doesn't the sine x use all the odd powers and alternates them? If you took the absolute value of this guy, wouldn't you destroy that -1 part? And if you took the absolute value of these two guys together and put them together as a single thing, don't you end up with e to the x? That's weird. There's a thing called De Moivre's theorem, which is e to the I theta. And it says that e to the I theta is cosine theta plus I sine theta. Right? If you take the power series and replace x with I theta in here, if you take this guy and just replace the x with theta, and you take this guy and you stick an I in front of him and replace the x with theta, these two together generate him. Which is what that is telling us is that, you know, e to the x, sine and cosine x, are very closely interrelated to each other. But they're interrelated in the complex world, the complex number world, which generates a whole branch of mathematics called analytic geometry. And we've discovered some very curious things. Do you know functions that we think we know? We're only seeing a piece of them as they hit the 2D plane. Can you imagine you did sine x and cosine x, but you allowed those values to be complex numbers, right? 2i plus 1. Imagine doing that. What on earth do those functions look like? They look totally different from what we think a sine and cosine does. Can you imagine the flat piece of paper being the 2D world? And that's what we see when we sine x. Can you have a third piece of paper going into the wall? Now you've got the complex plane. So what you're really doing when you see cosine x is you've put this wall of realness in front of you, and you're only seeing what it looks like as it hits the wall. If you look further back, the cosine function enters into a much more interesting place. For instance, do you know it's possible to get the cosine of x to be 2? You just have to pick complex numbers for x. Do you know the cosine function can go off to infinity? At least in the complex plane it can. So a lot of the things that we think we know about functions, what we really are seeing is what they are in the real world. Taylor series gives us some insight into that. If I see two power series and the power series look very similar to each other, then I'm going to then re-look at what those functions are and say, those two functions are related in a way I never thought. I think it just goes on and on. All right. So let's do an ugly one, uglier, or maybe not, who knows. Let's do that one, but I'm not going to center it at 0. That would be a Maclaurin series. I'm going to center it at 1. Okay. Now, why do I need to do a power series of this guy centered at 1? Why can't I do one centered at 0?
Because natural log 0 is undefined.
Right, and its derivative, which is 1 over x, is equally undefined. So can you see why there was a need, once Maclaurin done his guy, for Taylor to say, but I want to do this one. And he found out he couldn't, not by using a center at 0. So why don't we center it at 1 then? What's the adaptation? Basically, you just find all the derivatives at 1 and try and get a pattern. Okay, so this guy has a derivative which looks like that. The second derivative, oh, by the way, if you're going to differentiate, you probably call it that, right? Its next derivative is negative x to negative 2. Then third derivative is negative, well, it's now positive, right? Because 2 negatives make a positive. It's positive 2, but I'm going to write it as 1 times 2. The fourth derivative is going to be negative 1 times 2 times 3, x to negative 4. And I think I don't need any more after this. Do you see that there is a distinct pattern in the derivatives? Positive, negative, positive, negative. This thinking going on here, right? So I guess I should have planned this a bit better. The value at 0 is 0. The value at the first derivative at 1, I should be saying, is 1. The second derivative at 1 is negative 1. The third derivative at 1 is 1 times 2. The fourth derivative at 1 is negative 1 times 2 times 3. The fifth derivative at 1 is positive 1 times 2 times 3 times 4. I'm going to try and figure out what the nth derivative at 1 is, because once I know that, it's going to go there, and we are done. If we can find this, we're done. Okay, would you ignore that as a special case? In which case, all I'm going to do is maybe start at n equals 1 instead of 0, and that'll take care of that. It's positive, negative, positive, negative, positive, negative, right? Doesn't that get generated by negative 1 to the something? Now, there are two choices. One of them starts with a plus and then goes negative. One of them starts with a negative, then becomes plus. One of those two, and only one of those, is going to give me, and I say ignore that, it's a special case, is going to give me that pattern. So, which one is it? Top one, bottom one?
Bottom one.
Okay, let's check it out. If I want the third derivative, shouldn't it be positive? Right, I'm just doing this as one check. Well, if you do 3 plus 1, you get 4, negative 1 to the 4. We nailed it. So we're going to be using that guy. Now, what else do I have? Do you recognize these funny fellas? What's another way of 1 times 2 times 3 times 4?
4 factorial.
Okay. And won't this one be 3 factorial? Won't this be 2 factorial? This is 1 factorial, and you're just going to have to trust me. I'll call that 0 factorial. So The fifth derivative gives you 4 factorial. The fourth derivative gets you 3 factorial. Wouldn't the nth derivative give you n minus 1 factorial? Are we comfortable with that pattern? Haven't I now generated the thing that I need to know? The nth derivative at 1 is negative 1 to the n plus 1 times n minus 1 factorial. So you go over here and you do the nth factorial at 1, which is this guy. And then we have, well, we're actually using this guy, to be honest, aren't we? No, we're not. We're using this one. Take it back. You're doing x minus 1 to the n. Just check it out. Looks good. Well, could I make it look prettier? Is there something here that can cancel, simplify? Oh, forgot my 1. Oh, remember we had to ignore the first guy, so I'm starting at 1. And I don't know why I wrote that guy down again. Can you cancel these two guys? And if you do, isn't there an n left over in the bottom? So that guy doesn't need to be there. It's over n. So let me rewrite that guy nicely. N equals 1 to infinity. This fella, this guy, over n. And now I have the power series for log n, the natural log of x. Now, you can find that guy centered at 0. So what they did is, to avoid the 1 over 0 issues and the log of 0 issues, we find the power series of this guy. And if you find the power series of this guy, it looks like that. Yeah. Can you remember the alternating harmonic series? Remember the 1 minus a half plus a quarter minus a third? And remember I told you it converges, right? It's an alternating series and it converges. Can you remember I also told you it converged to log 2? Let's prove it to you. I'm going to use this version. I could have used that one, but I'm going to use this one. Now, if I use this one, if you plug x equals 1 in here, won't you get the log of 2? If you plug 1 in here, you get this power series. If you write this power series down, actually this one you can start with a 0. Do you see the alternating harmonic series? I think that's pretty cool. If you know where the power series comes from, you can actually find what the power series adds up to. For instance, see if I plug 3 in here, wouldn't I be able to find what the power series of whatever that looks like when x is 3? So it'll be full of 3s and 9s and 27s and various pairs of that. Well, that's a big challenge, but it's hopefully something that you can have practice at, but not much. What's the next thing you're going to learn? Well, because it is such a pain to generalize the formula written, very often they don't bother. Do you know what you do instead? You just find the first 4 non-zero terms. And we know that that very often is a very good approximation. So let's suppose I was asked to find, well, let's pick something that I already have pre-made, so I know it's going to come out relatively nice. Oh, can't find one. Right, there it goes. F of x is equal to x e to the x. And I don't want to try and find the generalized power series because I'd probably go grey-haired and very frustrated, because trying to find the nth derivative at 0 is a very taxing job. It's sometimes pretty much impossible to see one. So I'm not going to. What I'm going to do is just find the first 4 or 3, I'll figure it out in a minute, centered at 0, because that's the easiest one to do. Okay, f of 0 is 0, so that one isn't usable. If you do a differentiation on this, you will get 1 times e to the x plus x e to the x, which gives you 1 plus x e to the x, and its derivative at 0 is 1. Okay, so I can use that one. The second derivative of x, which is this guy, what does that get you? It gets you 1 e to the x plus that guy. It gets you 2 plus x e to the x. And so the second derivative at 0 gets me 2. Oh, I think I can do this one. That fella, pretty sure now that I see a pattern. And I've got 1, 2, 3. Guess I just need one more then. Now, you might, and I hope you're saying, how on earth is he going from that to that to that? Do you know I am not differentiating them really quickly in my head and writing the answer down? I'm just making the assumption that there is a pattern. And if I see something 2 or 3 terms, I normally can say, ah, there is a pattern. I'm pretty sure I know what the next derivative is by using the pattern. Can you see the pattern here is just add one more? Right, so won't the fifth derivative be 5 plus x e to the x? Right. We're ready to go. So what is f of x going to look like? Well, if you write this down, it looks a bit weird. You get the 0 derivative at 0, x to the 0 over 0 factorial. That's weird. Then you get the first derivative at 0, x to the 1 over 1 factorial. That's much more sensible looking. Then you get a second guy that looks like this. And since I'm running short of room, I'm only going to do the third guy. It looks like this, but there'll be a fourth and a fifth. Okay. Pause on that one for a minute. He's weird. The first derivative at 0 is 1. X to the 1 over 1 factorial. Well, basically, that's what you get, right? If you do the second one, you get a 2. X squared over 2 factorial. If you do the third one, you get a 3. X cubed over 3 factorial. And if you do the last one, you get a 4. X to the 4 over 4 factorial. All right, let's look at this guy. What is x to the 0? 1. Great. Can you trust me that 0 factorial is 1? It looks like it should be 0, but can you just trust me it is 1? And that's just math magic, and you're just going to live with that. What does this funny thing look like? Well, it's not really intuitive, but do you know that zero's derivative of f just means f of 0? That's all it means. Which in this case isn't f of 0, 0, so all that disappears, so there's nothing there. So there'd be a 0 here, right? Now, since you're going to be asked to find the first 4 non-zero terms, do you see I've got them? I needed to get 5 because one of them was 0. Do you know in some questions, every second one will be 0? So if you have to get 4 non-zero terms, can you see you might have to go out to the 7th or even 8th derivative before you could find 4 guys out of the 8 that are not 0 terms. Now I'll tidy this up a little bit. That guy's basically x. 2 and 2 factorial. In my book that gets you 2. 3 and 3 factorial, well that gets me x cubed over 4. And 4 factorial and 4, that gets me 3, 2 and 1, that gets me 6. Technically speaking, it's not equal to it. It's approximately equal to it. So I should be able to use this guy instead of x e to the x. So this fella behaves very like that guy. And I'm making the assumption that the first 4 terms are where most of the value is. So I'm now about to take my mathematical career in my hands and risk being shown that it ain't that good. I am going to find 0.1 e to the power of 0.1. In other words, I'm going to evaluate this at x equals 0.1. According to the calculator, 0.1 times e to the power of 0.1 is 0.1105170918. Now, if I'm going to use this guy, then won't I be evaluating, let's see, what am I going to be using? I'm going to be using 0.1 plus 0.1 squared divided by 2, 0.1 cubed divided by 4, plus 0.1 over 4 with a 6. Agreed? Now, when I did e to the power of 1, I got 2.66, and the right answer is 2.72, so not a great bet. Do you think this one's going to be better? If I'm good to 2 decimal places, will we call that a victory? How about 4 then? You're engineers. What's going to make you happy? 4? If I get it, say to there, and it matches, will you be happy? Maybe you're never going to be happy. I'm going to say you're happy on 4 then. So here goes. 0.1. Move this up a little bit, and maybe you can see my calculations. 0.1 plus 0.1 squared divided by 2 plus 0.1 cubed divided by 4. Just notice something. 0.1 plus 0.01 divided by 2. Just in case it thinks it does the power and divides by 3, just making sure the orders works. Plus 0.001, which is what that guy is, divided by 4, plus 0.12, 3 of these guys, 1 divided by 6, and the answer is 0.105. And some stuff. Hey, if I round off, don't they at least agree to the 1-1? I think my maths reputation is getting a bit of a knock there. What's the problem? No problem. Don't I just maybe need 8 terms rather than 4? I just need to do more polynomial. Now, you know you don't do that by hand anyway. Won't you write a little program to use the first 20 terms or the first 2,000, whatever you think? And then you can get as accurate as you want. So what's next? Well, let me find a little piece of paper that I'm going to use now. You can let someone else, what's over here, do the heavy lifting for you. There is a whole table that you can go look, and these are just some of the members of that table, where someone has already done the Maclaurin series for you. And you can use that to find the power series of other functions. So, for instance, I would like to know the power series of cosine of x squared. Well, I know the power series for cosine x. All I need to do then is substitution. Don't think of that as x anymore. Think of that as a placeholder where you put things. So if I put x squared here, shouldn't I put x squared here? So I have -1 to the n, x squared to the 2n over 2n factorial. And that you just basically do a little tidying up. Raise that to the power of 2, you basically get that guy. And suppose I want that guy. Then don't I stick an x cubed in the front? And then can't I bring that inside? And when I bring it inside, I essentially just add 3 more. In fact, if you take any function and you multiply it by x, don't you just add 1 to the power of its power series? And if you x squared something, don't you just add 2 to its power series? And so on and so forth. That's a little bit easier to deal with, isn't it? If you let someone else who's figured out the hard stuff, which is this, and then you just do substitutions. Power series for the inverse tan function. Inverse tan function is -1 to the n x to the 2n plus 1 over 2n plus 1. Now, I would like to know the inverse tan of x cubed with an x at the front. Then it's going to have an x at the front. Replace the x with x cubed. All I did there is 3 times that, right? X cubed raised to the power of 2n plus 1, you multiply these. And then I'll bring in an x. Which basically just adds 1 more to the power of x we have. And you now have the power series for x inverse tan of x cubed. So as long as you have a building block, you can do pretty much any kind of guy that you would normally expect to see. Right, you got a chat, what's up? Whatever that is. Let's see if I can show you so I don't have to write it. Are you here somewhere? Ah, here we go. There's a list of the pretty much the basic ones that you're likely to need in some of your homework questions. In the homework questions, you just click a little tab and you get to this page. And if you've got that, can't you now find the sine of x cubed, the cosine of x squared, the inverse tan of, I don't know, 2x plus 1. Right, if you were doing the inverse tan of 2x plus 1, wouldn't you just replace all the x's by 2x plus 1? Right, that's pretty much all you do. There's the natural log of 1 plus x. And won't really worry about the bottom one. It's called the binomial expansion, and it's got some terms. And that's probably the only one I wouldn't be too concerned about. I kind of like my friend there, e to the x. I'm not quite sure why 1 over 1 minus x gets top billing. I think e to the x is just more interesting. I would have put that one at the top, but that's just cosmetic. Are we cool? Now, I haven't even mentioned intervals or radius of convergence, but won't you just do the ratio test like we did a whole day worth of, and you get the answer that way? So that part of the process is, I think, isn't that much. Okay, now where the heck is this? That's here. So do I go back or do I cancel? I cancel. Is there any questions so far? Is there something that you'd like me to try another way of saying? Are we good? So, I think you'll probably find out that I'm right. Of all the things that you're going to do in that section, the hardest part is going to be to find from scratch the pattern for the nth derivative at 0 or the nth derivative at pi. That's going to be the one that will kill you. But hopefully you'll be able to figure out that. If you're good at pattern detection, it'll probably be quite easy. And we're now on to our last section. Wow. There should be a fanfare or something when you do something like the last of anything, shouldn't there? There should be, but there's not. I'm trying to find where we are in this multitude of screens that I have in front of me. Okay, so the last section is called applications of Taylor's. So it's going to be 11. I'll just call it applications. Because actually, Maclaurin does get applications too. Now, let's show you stuff we already know or have seen before, but it still counts as an application. If you take a function like e to the x, you can do its power series. I've used this one a lot because oops, there we go. Is that guy? Now it's kind of difficult in the human world to use a calculator and do an infinite polynomial. So I'm not going to try. What I can do, however, is couldn't I take this polynomial and just do maybe 4 terms? So we have a technique or a naming system. T4 of x is what you get when you take this guy and you go all the way to the n equals 4 value. So in this case, it would be 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial and finish x to the 4 over 4 factorial. Do you see that that actually has 5 terms in it? So T4 means you go as far as n equals 4. Now in this case, n equals 4 gets you that guy. Suppose f of x was cosine of x. Well, you'd go and look at the formula for cosine of x in its power series. Looks like this. Actually, I think that was the one we created, wasn't it? Now, what would T4 of x look like that? Well, if you plug in 0, you get 1. And then you get negative x squared over 2 factorial. And then you get plus x to the 4 over 4 factorial. Now, in this case, T4 of x indicates that the highest power of x is 4. It doesn't indicate in this case that you use n equals 4, because in this formula aren't half the terms zeros. So if somebody says to you, I want T3 of x, maybe it'll mean n equals 3, maybe it'll mean n equals 6, maybe it'll mean n equals 1. What it means is you only do the power series up to x cubes. If you see T5 of x, you only do the power series up to the x to the 5 term. Because some formulas, that means you use everybody. In other formulas where there's only certain powers that exist, that is going to happen. To give you a weirder example of that same rule then. This is what sine x looks like as a power series. If I try to do T4 of x, right, I'd plug in the first number, which is x. That's what you get when you plug in 1. If you plug in 2, you get x cubed over 3 factorial. If you plug in the next one, you get positive x to the 5 over 5 factorial. If you plug in the next one, it looks like that. Right, but back to the question. They wanted this guy. That is not this guy. That is T7. Why is he T7? Because the biggest power is x to the 7. So it ain't that one. Well, what about these 3 guys? Nope. That's T5 because the biggest power of x is 5. Then what about this guy? Yes, but he doesn't have an x to the 4. Well, if you want to be nitpicky about it, he does. So can you see that some T4 of x's might not have x to the 4 in them? That's T4 of x for that particular function. Okay, so as a naming system, it's a little bit clunky, isn't it? Because it doesn't mean there's going to be 4 bits. It doesn't mean that the highest power is x to the 4. It doesn't mean you plug in n equals 4. It means you go as far as x to the 4, and if there isn't an x to the 4, you go as far as you can get without it then. Now you try and put that into English, it doesn't make a lot of sense, but do you get the gist of what T4 of x is? Right? For instance, do you know what T5 of x is for this guy? Same thing. Doesn't this guy not have an x to the 5 term? So won't its T4 and its T5 be the same fella? So that's a little hiccup. Right. Now the cool stuff. I am going to put into the calculator cosine x. And I'm going to put in this fella. 1, take away x squared, divided by 2 factorial, which is 2. And then I'm going to add x to the power of 4. And I'm going to divide it by 4 factorial. 2 times 3 times 4 is 24. I'm going to choose a window. I'm going to choose a small window, negative 0.1 to positive 0.1. And now I'm going to just do a zoom to fit. And okay, what did I do wrong here? That looks perfectly fit. Is it my function? Interesting. Well, very nice, but interesting. 1, take away x squared. Oh, yeah. Have you noticed that I still don't swear much, even when I probably should? It ain't that hard to type in x squared, but evidently my brain is not allowing me to do it. So, there, we gotcha, I hope. And then it's x to the 4. I'm trying to divide by 24. And that should simply just work. Yay, it does. Now what you're looking at is what cosine x looks like, at least between x is negative 1 and x is positive 1. Do you only see one curve? Well, actually, do you know you're seeing 2 curves, but they're on top of each other? Now, look, you see I've got 2 different things being sketched here. So that's an application, if you like. Can't you use the T4 of x or the T3 of x, whatever it is you're using, can't you use that as a replacement for your original function as long as you keep close to 0? But let's move out a little bit further. How about negative 0.2 to positive 0.2? And I'll do a zoom to fit now. Okay, that's just the cosine doing his thing. Would you agree it's a pretty good fit? Okay, let's put it under stress. Negative 0.5 to positive 0.5. Nothing. Doing a good job. Okay. Negative pi divided by 2. Positive pi divided by 2. Do you think the 2 might start separating now? Can you see a slight thickness at the ends? Can you see they're beginning to drift? But not much. Doesn't that mean that the polynomial that I wrote down here is a very, very good fit to the cosine function, at least between negative pi upon 2 and pi upon 2? It's pretty cool. This is going to kill it. I know it is. How about negative 2 pi to positive 2 pi? This is the last one. Yeah, it died. Can you see that at the ends now, it's so bad the poor cosine is crushed into a little window at the bottom. That little ripple at the bottom is, by the way, the cosine, right? So a couple of things that we're showing you in this is that couldn't you use as an application a polynomial instead of the original function? And as long as you keep whatever relatively close to zero means, you should be able to get good answers and a pretty good approximation to the entire shape. Now, I'm trying to see where the heck I'm going here. And this may or may not work. So just hang in there. If it doesn't work, that's fine, but it would be cool if it does. We're looking, or you should be looking at your homework. It's got a little simulation at the top. You seen it? Now, here is the function called 1 over 1 minus x. And here we have a kind of Taylor series, and n equals 5 and all the various colors going from that. Now, if I hit a little animate, that's very fast. Let's go back. Right. There's T2. Do you see that the two of them kind of are okay in the middle, right? But they drift quite quickly. If I move up to T6, you see that the fit is a little bit more, and then it starts losing it. The black guy is I'm assuming the black guy is the original function, and the red guy is Taylor's approximation to it. If you go 8 or 12 or all the way to what there, 12, can you see that it's pretty good on this side, but it kind of loses it really badly on the other side? So what we have here, worked quite well. Let's see if I can do another function. Inverse tan. Can you see the inverse tan behaves very much in unison with the polynomial until you get to about here and you finish it here? And then almost like it fell off a cliff. And you might think, what is so important about 1 and -1? Remember the interval of convergence? If a power series only has an interval of convergence from -1 to 1, shouldn't you only use it with numbers inside that range? And you can imagine then, well, what's going to happen when you go beyond that? The thing diverges off to infinity and it doesn't match it anymore. So what you're seeing here is a visual representation that the interval of convergence here is 1 to -1. The 3 basic power series interval convergence that you'll see a lot. The best one is e to the x, and ones like it. Interval of convergence, -infinity to +infinity. Next tier down, -1 to 1. Inverse tan, for instance, does that. Right? You can only use it if x is between -1 and 1. Last one. Since every function in the universe can be written as a power series, some poor functions can be written as a power series, but only have an interval of convergence of the number x equals 0, which basically means that their power series is useless. So you're going to be looking at various versions of power series, like T1, T2, and looking at their graphs, which is kind of happening here. And then they talk about this thing called Taylor's inequality. And basically, Taylor's inequality gives you an idea of what the error would be. So if I had a Taylor series T4 and I was using it to approximate sin x, when x is 1.4, what would the error look like? And that's basically what this fella here is. It's the remainder function to x. That would be the one that you would get with T2 of x. And I am going to put some notes on how to calculate that guy. And it's just basic number crunching. It's awkward rather than difficult, in my opinion. And basically the same question every time. Here's a cosine, find T of 3 of x, tell me which picture it is. Right? Well, it's one of these pictures, isn't it? Do you know what T3 of x looks like? Did we do T3? I think we did. T4, didn't we? Right, let's bring this guy back. Here's T4 of x. What will T2 of x look like? Oops. You can't see this. There's T4 of x. What will T2 of x look like?
One minus x squared over 2 factorial.
Right. Won't T3 of x look like that as well? So can you imagine you do a picture of cosine x, and on top of that picture, using your calculator, you do 1 minus x squared over 2 factorial. Won't you get one of those pictures that you no longer can see, and that's the guy you pick? So just knowing that, shouldn't I be looking at a quadratic that is concave down? So one of those pictures will look like a quadratic concave down, and that's the one you choose. We got time for, yeah, we got time for another application. Okay. The sine of x, if you write it down in its, I'm thinking cosine here. If you take the sine of x and you write it down, it looks something like this. Agreed? If you put it in. Now, here's an application. You know that we could find the limit of that with L'Hopital, can't we? And if I did it with L'Hopital, because it's in determinant form, I should be able to do that, and I am allowed to. Don't I get the cosine of x over 1? Then I plug in 0, and we get 1. Well, if this is sine x, shouldn't I be able to do what sine x over x looks like? Well, can you imagine I'm taking all of this and sticking it over an x? Won't you basically just reduce each of these powers by 1? So this guy is 1. This guy will become x squared over 3 factorial. Then it's going to be an x4 over 4 factorial. Then it's going to be an x to the, oops, right down here, x is 6, that's better, over 7 factorial, plus or minus forever. Now, can I evaluate this at 0? Oh yeah, because won't those all be zeros? So what's this at 0? It's 1. So if I had a really, really ugly, and I'm not even going to do it, but can you imagine I had some really ugly looking thing like that, and I was going to find the limit at an indeterminate point, which will probably be 0, right? Can you imagine trying to do L'Hopital with that? Might not end well, or at least it could be, well, let's make it even harder. No, that's hard enough. Couldn't you find a power series? I mean, not all of it. Couldn't you just find the first 3 terms of this guy? Couldn't you find the first 3 terms of that guy? Couldn't you divide them all by x squared? And let's just pretend that the answer ends up looking something like this. Right, whatever it is, right? Wouldn't you just be able to say, 7/3. Now, do I need to do many of these? No. Isn't it only the constant term that's going to be important? So if you're dividing by x squared, you probably need three or four terms just to be on the safe side. Can't you just multiply a cubic with another cubic and then divide it by x squared? And can you imagine this is what you would get? Can't you now find the limit as x tends to 0 by using approximate power series, right? Just using some of the terms. I don't care what the other terms are, because aren't they going to be bigger than x to the 4? And won't all of them disappear anyway, so, you know, who cares? Yeah. Another application. Take a little bit further than they did. I'm just going to make this up. Imagine you have physics and you have a formula that looks like 1 plus 1 over c squared cubed and some other weird stuff, right? And they say to you, when c is really close to 0, this is the same thing as that. You ever seen the, sometimes in physics they say, for very large values or for very small values, this function behaves like this much simpler one. Right? Very often when you do classical physics, right, Newtonian ones, right, and then you move on and you look at special relativity. Don't special relativity and Newtonian become essentially the same formula as long as you don't travel too fast? Right. So as long as your speed's relatively slow. So something that looks really ugly in relativity ends up just being, you know, V equals IR or something. Right. So how does that happen? Well, do you know what you do is you take a power series of this guy and you cube it, and then you just take the first two terms, and boom, you've got your answer. I can